Now that we know that alkanes will react with hydrogen halides, the question then becomes, what happens when the alkene is not symmetric? Remember, in the previous example that I showed, we were working with a symmetrical alkene, that 2,3-dimethyl 2-butene. So both carbons had the same groups coming off of them. What happens when the two olefin carbons don't have the same substituents coming off of them? So let's take a look at an example. Here we have 2-methyl propene. And notice the carbon on the right has two methyl groups, and the carbon on the left has two methyl groups, and the carbon on the right has two hydrogens. And so what's going to happen? Well, we can envision two possible pathways, and let's take a look at both of those pathways and see what the actual result ends up being. So we're going to react this with HCl, and remember the pi orbital, right? The electrons in the pi orbital are going to attack the sigma star orbital of that hydrogen chlorine bond. And so it's going to attack the hydrogen because that sigma star has more hydrogen character than it has chlorine character, right? In other words, the electron density resides closer to the chlorine and the hydrogen is electron deficient. And then once that bond starts to form, the electrons from that HCl sigma bond go to the chlorine. We end up then with one of two possibilities, one in which the hydrogen can go to the carbon on the left and one in which the hydrogen can go to the carbon on the right. So in the first scenario, I'll place the hydrogen arbitrarily on the left-hand side. The result is the other carbon becomes a carbocation. And then, of course, we know that the chloride ion is then going to add to that empty LUMO of the p orbital of the carbocation, and we end up with that addition reaction. Namely, so this would be 1-chloro-2-methyl-propane. That would be the product if this was the path that the reaction took. Now, another possibility is, again, taking our 2-methylpropene, reacting it with HCl. Again, our pi, the electrons in the pi orbital are going to attack the sigma star of HCl. And now this time, I'm going to put the hydrogen on the right-handed carbon, and the left carbon becomes the carbocation. So now the chloride could possibly attack that carbocation, and the result is this product, which is 2-chloro-2-methyl-propane. And so you see that we end up with two possibilities as products. Now, whenever you have this scenario where you can have two possible areas or regions of the molecule being attacked, this is called regiochemistry. And if one area or one region is selected over the other, it's called regioselectivity. It happens in this particular case, there is regioselectivity, in that only the second product forms. So only 2-chloro-2-methylpropane forms as the product. In other words, the first reaction doesn't occur at all. Now, why is that? Well, the difference between the two pathways is in the intermediate carbocation stability. Remember, addition, so that second step, the addition step, is not the rate determining step. The first step in our reaction mechanism in that formation of the carbocation is the rate determining step. And therefore, we have two different intermediates that are possibly forming. The first pathway, that intermediate looks like this. And if you think about the carbocation that is formed right here, this is a primary carbocation because it only has one carbon attached to it. In the second pathway, the carbocation that formed look like this, right? Now, this is a tertiary carbocation because there are 3 carbons attached to it. And what we discover is that, well, since these are the 2 possible intermediates, it must take less energy to produce a more substituted tertiary carbocation. And therefore, we can think about the stability of the carbocations. Remember, these still are not stable, but when you talk about a pathway in which a reaction can undertake, when you're looking at an intermediate, the more stable the intermediate, the faster the reaction goes because the less energy is required to actually produce that intermediate. And so we can actually plot energy versus the possible formation of that intermediate. And we see that for our tertiary carbocation intermediate, it's going to require a relative amount of energy. And for the primary formation of the primary carbocation intermediate, it's going to require more energy. And therefore, the tertiary carbocation is going to form more readily than the primary carbocation. Hence the regioselectivity, because as soon as the carbocation forms, remember, very rapidly the chloride is going to undergo an addition reaction. And so this is the key to understanding that regioselectivity. And we see that this in a variety of reactions, such that we can actually figure out the order of the stability of the carbocations, in that tertiary carbocations are more stable than secondary carbocations, that's a secondary carbocation, and secondary carbocations are more stable than primary carbocations, and primary carbocations are more stable than methyl carbocations. And therefore, if we can predict what type of carbocations are going to be formed in the as intermediates, then we can predict the products that are going to be formed in those reactions. And so let's look at a couple of examples here. Here I have 2-methyl-butene, and you see that if I think about the first step, right, the addition of the pi electrons to that sigma star of HBr, then I can form one of 2 possible carbocations. The left carbon is going to produce a tertiary carbocation because it has 3 carbons attached to it. The right carbon would be a secondary, produce a secondary carbocation. And therefore, I know the tertiary carbocation is going to be formed over the secondary carbocation, and the halide is going to attack that tertiary carbocation, and I end up with this regioselectivity. So the only product that I make in this reaction is 2-bromo-2-methyl-butane. Likewise, I can look at an example like this. Here I have 1-methyl-cyclohexene. If I react 1-methyl-cyclohexene with HCl, again, looking at the alkene carbons, this one would produce a tertiary carbocation. The one on the right would produce a secondary carbocation. And therefore, the tertiary is going to be favored over the secondary. So the chloride is going to attack that tertiary carbocation, and we end up with this 1-chloro-1-methyl-cyclohexane. And so now you have an idea about the regiochemistry of the addition of HX to an alkene.